And before we start and actually do all these physics and math, what I like to do is follow our professor's meta-analysis. And the questions that you need to ask are what type of load this is. And if you look at this question, we can tell that this is only a lateral. So this is a lateral. And is it a failure or deformation question? So the question is asking us where does the maximal upward deflection of the beam occur within segment AB? So this is not a failure question because it's not asking if it's going to fail or not. It's asking us about like, what's a deformation? So this is a deformation question. And then the third one is this uniaxial, continuously varying, or segmented? We can technically say that this is a continuously varying. You guys might think this might be uniaxial because there's only like one bar, but it's technically continuous varying because we have a distributed load on top here. And distributed load changes, like the force changes along the x-axis. Therefore, this is a continuous varying. And the last question we should ask is a forward question or reverse question? This is a forward question because forward question is basically asking, oh, here are the given things. What's going to happen, right? Is it going to deflect? What's the deformation? Is it going to fail? What's the stress? All those kind of things. What's going to happen, right? Reverse question is basically asking the reverse. Like, oh, this failed, or this is the deflection. What is the length? What is the original length? What is the force? But in this question, they're only asking us about the maximal upward deflection. So there's a forward. Question. So now that we did the meta-analysis, we now know which type of equation that we need to use, which is great. And the first things first to solving these type of question is always solve your support reaction first. So let's do the support reaction. If we draw the free body diagram of this whole beam, we have FA over here because this is pin. And then we have FB as a support reaction because it's a roller. And then we have resultant force because of the distributed load. And I'm going to mark this at A. And FR is going to occur at the midpoint because they are all uniform. Okay, using this, we can solve for FA and FB. That's the, solving the support reaction is. So let's start with FY. So positive FA plus positive FB, negative FR should be 0. And we know that FR is equal to the distributed load times the area or the length that the load is applied to. So which means FR is equal to Q, which is given, times the whole length, which is B. We can write FA plus FB is equal to negative QB is equal to 0. And because we do not know both FA and FB, we're going to solve for moment equation to see what we can do here. And you can say that moment occurring at point B is going to be positive using the right-hand rule. So it's A times FB. That's positive. And moment occurring at the resultant force is negative using the right-hand rule, right? So negative FR times the length is A plus B over 2. And that should equal to 0. And we can solve for FB. By solving for FB, we get that FB is equal to this. And we can plug this FB into our equilibrium in Y direction and get that FA plus FB is equal to QB. And plug this in and we'll get FA. And as you can see, we can distribute this and cancel out. So we get that FA is equal to negative QB squared over 2A. And I like to circle my support reaction because it's easier to refer to it later. And then now that we have solved support reaction, we're going to solve for internal forces. That's the second step. So you might be asking me, then where should we cut it? Like which type of internal force that we need to look at? The thing is, we don't have to cut anywhere here or like we don't have to make any segments because the question is asking only at the maximum upward deflection at segment AB. So we only is just thinking about AB. We don't have to think about BC. So let's cut at X in between section AB and let's solve for the equation. And here is X and we're going to cut it here. And don't forget that there is support reaction FA. And then we can solve for Vx, but it's really not necessary here. So we're only going to solve for Mx because it's only asking for us about deflection. We only need Mx, right? So doing so, we can solve for Mx also using equilibrium equation. Is Mx is in the positive direction, right? So write Mx, and you might be confused of like where I need to, regardless if the x direction is like this way, like to the right or the negative, but always in terms of internal forces, like the 0 is here when you cut the beam. Therefore, the x direction should be over here, pointing to the left. So using the right-hand rule, this moment at point A, because of the internal force, is going to be negative. It's going to be negative x times FA, right? And that should equal to 0, meaning that mx is equal to xFA. And good thing is we already solved for FA in the support reaction, so we're going to plug that in. X times negative B2A. Great. That is our moment equation. So mx equals negative x, b cubed q2a will be our moment equation. Now that we have the mx, we can write the small angle beam equation. And we want to know deflection, and deflection equals Vx, which means we need to take a double integral of this equation to get Vx, right? So let's do that. Let's first take the integral of this equation, and we'll get dv dx, right? dv dx is equal to, and then Vx is equal to here. So now that we have this equation of deflection, you might be wondering, how do we actually figure out what the C1 and C2 is? Because this equation is not complete. Well, good question, because we are going to use boundary condition value, like initial value problems in integrals that we did long time ago. Deflection at that point is going to be 0. Which makes sense because they have support, so there should not be any deflection, right? So if we make this point 0, then deflection at point A, which is x is equal to 0, should be 0. And this is the length of A, meaning that this should be the deflection of point B, VA should also equal to 0. That is our boundary condition that we can use. Writing it down again, V0 equals 0, and VA equals 0. And we are going to plug that in to get C1 and C2. In order to get the maximum deflection, we need to know that dv over dx is equal to 0, because maximum deflection, if you think about it, this is where the maximum deflection happens, which means the slope at this point is 0. So maximum deflection is where dv over dx is equal to 0. Does that make sense? So instead of using this equation, we're going to plug in C1 back into our dv equals dx equation over here, and then set that equal to 0 and find what x is. That's the point where there is a max deflection at section AB. So let's just do that, just algebra now. AQ, so is x. And x is equal to root 3/1 times A. And that is our answer. Thank you.